Good evening. അപ്പോൾ നമ്മൾ ഫസ്റ്റ് ചാപ്റ്ററിൽ തേർഡ് ചാപ്റ്ററിൽ ഫസ്റ്റ് സെക്ഷനിൽ നമ്മൾ ഡിസ്കസ് ചെയ്തത് എന്തായിരുന്നു? പവർ സീരീസിൻ്റെ കുറച്ച് കണ്ടീഷൻസ്, അതുപോലെ പ്രോപ്പർട്ടീസ്, പിന്നെ നമ്മൾ റേഡിയസ് ഓഫ് കൺവേർജൻസ് കാൽക്കുലേറ്റ് ചെയ്യാനുള്ള രണ്ട് ഫോർമുലാസ്, അത് ഒന്ന് തിയറമായിട്ടും ഒന്ന് പ്രപ്പോസിഷനായിട്ടും നമ്മൾ ഡിസ്കസ് ചെയ്തു. Now we are moving to the second section of section 2, second section of this chapter. That means we are moving to the second section of the third chapter. The second section is about analytic function. So everybody knows the idea of a function. So when we can say that a function is analytic? So to define an analytic function, we need the differentiability of the function. So first we have to review our previous knowledge. So first we define when we can say that a function is differentiable on an open set. To define the differentiability, we need an open set at which the function is defined. To define differentiability of a function f, we need an open set at which our function is defined. So consider a function f from G to, now we are in R2 plane, that means in the complex plane, so complex valued function, so our codomain is C. G is an open set. What is meant by an open set? Open set means you already studied about the open sets in your real analysis, first and second some real analysis. So here in order to define an open set, we need a metric space. So here our G is an open set. Open set means every point in G is an interior point. You know the idea. So suppose f is a function from an open set G to the set of all complex numbers. This function f is said to be differentiable at a point A. First we want to define the differentiability of a function at a point. Suppose we take a point A from the open set G. Then when we can say that this function f is differentiable at this point. So to define a differentiable function, we need an open set at which our function is defined. This idea you have to keep in your mind. So suppose you take a point A belongs to G. We can say that this function f is differentiable at A if everybody knows the idea. If limit h tends to 0, f of a plus h minus f of a divided by h. If this limit exists, then we can say that our function f is differentiable at this point. Is it clear? Limit h tends to 0, f of a plus h minus f of a divided by h exists. So we can say that f is differentiable at the point A. When will we can say that? And now usually there is one question in our mind. When will we can say that a function is differentiable on a set? So here we take the set as G. So when will we can say that our f is differentiable on G? F is said to be differentiable on G if this f is differentiable at each point in G. F is differentiable on a set G if it is differentiable at each point of that set. Okay. So it is differentiable on G. When we can say that a function is continuously differentiable? A function f from G to C, G is an open set, is said to be continuously differentiable. You know the idea. If f is differentiable at a point A, then f dash of A exists, and if f is differentiable on G, we can say f dash. Also, what about what idea you have in your mind about this function? This f dash, is it a function? Yeah, f dash is also a function. If f is differentiable on G, then your f dash is also a function from G to C. This also you have to keep in your mind. If f is differentiable on a set G, then f dash is also a function from G to C. If this f dash is continuous, then we can say that f is continuously differentiable. If this f dash is also differentiable, f dash is also differentiable, then we can say that f is twice differentiable. If f dash is also differentiable, then we can say that f is twice differentiable. So when will we can say that a function f is infinitely differentiable? When will we can say that a function f from G to C is said to be infinitely differentiable if each successive derivative is differentiable. F dash is differentiable, f double dash is differentiable, f triple dash is differentiable, etc. If this process occurs, then we can say that f is continuous, infinitely differentiable. So there are two ideas you have to keep in your mind. When will we can say that f is continuously differentiable? Infinitely, and f is infinitely differentiable. Okay, so f is, we discussed about f is infinitely. When will we can say that this function f is infinitely differentiable? Now you studied many results connecting this differentiability and continuity of function. Every differentiable function is continuous. Every differentiable function is continuous. But continuous functions need not be differentiable. You need to find out one example for a continuous function which is not differentiable. You studied in your real analysis. Okay, you have to find that example. Also, you have to check whether your mode function f of x is equal to mod x. What about this function? Is it continuous? Is it differentiable? That you need to check. Okay, so continuous function need not be differentiable, but differentiable functions are continuous. How we can show that a differentiable function is continuous? Suppose f from G to C is differentiable on G. We need to show that this f is continuous. How we will show that this f is continuous? To prove this f is continuous, you just take a point A belongs to G. What is the idea for showing this f is continuous at this point? You need to verify the condition that limit x tends to A, f of x is equal to f of A. This is the case of real analysis. Here, limit z tends to A, f of z is equal to f of A. To prove f is continuous on G, you just take a point from G, arbitrary point from G, and let it be A, and then to prove it is continuous on G, we have to show that limit z tends to a, f of z is equal to f of a. How we will show that this is true? So to prove this, you have one point, you have give one condition. This function is differentiable. This function is differentiable means it is differentiable at each point of G. So what will happen to this we need to show. So limit z tends to a modulus of f of z minus f of a. You need to show that the limit of this function when z goes to a is equal to f of a. That means to prove this, we consider limit z tends to a modulus of f of z minus f of a, which is equal to what? One condition you have to, they give one condition for proving this result. Which condition they given? F is differentiable on G. So you just connect with the differentiability of the function. So limit z tends to a, this we can replaced by limit z tends to a modulus of f of z minus f of a divided by z minus a into, so here we have one excess term, limit z tends to a, z minus a. So we need to cancel that term. So you just multiply with that term, limit z tends to a modulus of z minus a. What about this limit? This is f dash of a. Since f is differentiable on G, it is differentiable at each point of G. So it is differentiable on A also. So f dash of a exists. Into what is this? Limit z tends to a modulus of z minus a. This is equal to 0. So this equal to 0. So what is this limit? Limit z tends to a modulus of f of z minus f of a is equal to 0. So this is equal to 0 means what? This is equal to 0 means f of z tends to f of a as z tends to a. That is limit z tends to a, f of z is equal to f of a. That means f is continuous at the point a. So if f is differentiable on G, it is continuous on G. The reverse need not be true. That you have to verify. So what is the relation between an analytic function and a differentiable function? In your 6th sem complex analysis, you studied about analytic functions. Yes. So here what is meant by a function? Suppose you have f from G to C and G is an open set. When will we can say that this f is different? F is analytic at a point A belongs to G. F is analytic at a point A belongs to G if your A has at least one neighborhood. At each point of this neighborhood, f is differentiable. So f is analytic at a point A belongs to G if we can find at least one neighborhood for this A. What is the nature of that neighborhood? At each point of that neighborhood, f must be differentiable. So you need to find out at least one neighborhood for this A. If you got such a neighborhood for A, we can say that f is analytic at the point A. F is analytic at A. So when will we can say that a function is analytic on a set G? Here your G is an open set. So this f is analytic on G if it is analytic at each point of G. Yes. So another question is when will we can say that a function is analytic on a set? That set need not be, suppose you take this set S. S need not be open. S is not open. S is not open. So when will we can say that F is analytic on this set? I already told you that in order to discuss the differentiability of a function, you need one open set at which your function is defined. So when we define the analyticity of f at a point A belongs to G, you use the idea of differentiability to define analyticity. So when will we can say that f is analytic on a set? Yes, that set is need not be open. So f is said to be analytic on a set yes if we can find an open set containing S at which f is analytic. F is analytic on S if there exists an open set. If there exists an open set A containing S